Good afternoon. My name is Jeroen Mulder, and I want to welcome you to another presentation in our series of AI for aviation sustainability. Please note that this webinar is being recorded. Today's presentation is called Improving Trust in the Results of Search-Based Optimization. It will be presented by Dr. Sandy Brownlee, who is currently lecturer at the Division of Computing Science and Mathematics at the University of Stirling. Any questions during the presentations can be addressed through the Q&A section inside the BlueJeans interface. We will answer these at the end of the presentation. And today's moderation will be done by Astrid and me. Okay, that's it. We'll now give the floor to Sandy.
Hi, everybody. Thank you very much for inviting me into this talk, Jeroen, and I hope that everyone finds what I have to say interesting. So my background is in optimization primarily and machine learning, and I've grown very interested in this idea of trust and explainability over the past few years. So I've got a few things I'd like to share with you on that, and I think this is the point at which I share my screen, so I will try to do that. Hopefully we can see that. Is that coming through okay?
Yes, it is. Thank you.
Excellent. Right, so there's the title, and that's my name. Our outline is that I'm primarily going to be focusing on evolutionary algorithms and the broader family of tools that are known as meta-heuristics. So I'll give a very brief introduction to that. And then we'll take a look at what might happen when it goes wrong. Why might we not trust the results that evolutionary algorithms can give us? Because they're very powerful tools, but sometimes they get it wrong. And then I'll go into a number of different examples of explanations and providing informed choices to the decision maker. The first few are in a building design problem. I jokingly refer to that as my concrete example because it's a little bit easier to understand. Everybody knows what buildings look like. Before I'll go into a little bit of stuff that I've done with KLM, looking at tuning some software automatically. And finally, I'll conclude with a couple of examples around how we deal with multiple objectives and how we visualize some of these things. So to begin with, I'll give a little introduction to evolutionary algorithms. Hopefully this is a familiar concept to most people in the audience, but just so we're all on the same page, an evolutionary algorithm or a genetic algorithm basically is a general purpose solver for optimization problems. And the way that it works is that we have what we call a population of solutions. I'm hoping that you can see my mouse pointer. But the first row here is one solution to our problem. So on the left, we've got some ones and zeros, and there are our problem variables, our decision variables. These are the things we're trying to change in order to influence the quality of our solution. So they might be allocations of people to jobs or aspects of a design or parameters in a piece of software. Whatever it might be, these are the variables that we're seeking to tune. And the number on the right is some kind of a fitness score. It's basically a measure of how good our solution is. And what we do is we generate a few of these at random. So here we've got 6 solutions, and they've all got an associated fitness with them. Now here the score is a very simple one. It's just a toy problem. We just count how many ones there are in the solution. So the top one there, the best one, has a score of 4 because we've got 4 ones. And the way an evolutionary algorithm works is that we will pick a couple of the best solutions. So here we've picked the top 2, and we will swap them around. So this is at least in part inspired by natural selection and inheritance that you see in biology. So we have 2 solutions and they act as parents. We swap parts of them around to create 2 new solutions, or what we call offspring. And we might have some random variation as well, some kind of a mutation. So you can see I've flipped a 0 to a 1 in the second solution there. And they go into a new population and they get reevaluated. So that, as it would happen, one of the solutions has come out a bit better. One of them is mediocre still, it's still a 3. You'll find that sometimes we generate better, sometimes generate worse solutions. But we repeat that process over and over to create a new population, and that replaces the old one. And then we repeat that process a number of times, usually of the order of hundreds or thousands of times, until we converge on something that's pretty good. And now these processes are not guaranteed to produce an optimal solution, but they will generally do quite a good job for most real-world problems, and they're very successful for combinatorial and continuous optimization problems. Now, it's quite important that we're kind of on the same page with how these work, so I'm just going to check to see whether anyone's put any questions in so far. I don't see any indication of it.
No,
I don't. No, nothing.
There are no questions so far.
Right.
Good stuff. I think it's a kind, it's time to remind that, please feel free to ask your questions in the Q&A section, and we'll address them later.
Sure. Right. I'll pause a little bit later on in the talk as well. So by all means, if you get a question, post it, and then we'll, at an appropriate point, we'll try to answer it for you. So that's all very good. The problem with these approaches is that they only maximize fitness. All they can see most of the time is this feedback that they're getting in the form of how good solutions are. And they do a really good job of maximizing fitness, however it's defined. Sometimes we don't actually formulate that fitness very well, or we might have other goals that are just implied. So I've got a couple of amusing examples. A really nice paper. I've provide the link to it at the bottom in a moment, of examples of machines finding shortcuts. So genetic and evolutionary algorithms are really good at finding shortcuts in your problem definition. So here's the first example. So the idea here was that there was a group of researchers, this is not my work, who were using they were trying to simulate a robot, and they were using a genetic algorithm to evolve the design of that robot so that it would travel very quickly across a simulated surface. And what happened in this case? What did the genetic algorithm do? Well, I really like the creativity of this solution. What it did, it didn't make a robot with lots of legs. It didn't make one with very efficient operation. It made a giant leg and placed it at one side of the space, and then just let it fall over. And in a single move, it reached the other side of the space. So it was very quick, but it was not what was had in mind. The link there is down at the bottom to that paper, The Surprising Creativity of Digital Evolution. It's a really nice paper, and it's got some more examples. There's another one that comes out of the same paper, which is to do with what's called generalized tic-tac-toe, or noughts and crosses, as we call it in the UK. And the idea of this game, rather than the 3x3 grid, is that you're trying to get 5 in a row, but the grid is of an unlimited size. And if you're a quick reader, you might have seen the text on the right already. But in short, what was happening was they were using an evolutionary approach, again, to generate an AI strategy for the game and playing it against other existing AI opponents. And what happened was the evolutionary algorithm worked out that the way to win the game was simply to place your move as far as possible from where the current pieces were on the board. And what that would do is cause an out-of-memory exception in the opponent, so they would forfeit the game. And again, not exactly the kind of strategy that was had in mind when they were trying to design the game. Another example, and this one doesn't come out of that paper, but this comes out of the search-based software engineering community. So here they're applying, again, these evolutionary approaches, try to evolve bug fixes or improvements to pieces of software. And here they were trying to bug fix sorting algorithms. So fairly fundamental piece of code in computing is to sort numbers or objects into ascending order, and much simplified version of how it was framed is shown here. So they basically had an evaluation routine that would take the improved piece of code, and it would check that it had sorted the numbers correctly. So it would look at the numbers that had gone into the function, and it would sort them into it would count how many of them were in ascending order. So if they were all correct, then it would be cost 0. If they were in descending order, in this case, there's 4 neighboring pairs of numbers that are the wrong way around, so they get a score of 4. And that one at the bottom is fairly random, and the cost is 2. afraid I've given away the little surprise already. The algorithm took a bit of a shortcut here, and it was simply this. It just deleted all of the numbers. And, well, in one sense, that's correct. An empty list is sorted, but that again isn't exactly what was intended. And it's just because the fitness function didn't accommodate everything that was actually desired. There was no check in there to make sure that the numbers that were in the original list was still being was still included in the sorted list. So what's going on here is that the algorithm is just looking for patterns that are minimizing or maximizing our goal. They're just seeking to maximize this concept of fitness. And that's great, and it produces some really fun things like the examples that I've shown you. But if we're trying to use these algorithms for something more serious, then that can be a real problem. How do we know when we are actually solving our problem, or when the algorithm has just found a loophole in our definition? How do we know that we can trust the solutions? Because essentially the genetic algorithm is just a black box. In much the same way as we're seeing amongst the AI and machine learning community, where you've got deep learning models that are making decisions, and they're essentially producing answers as far as the humans are concerned, like magic. There's just a decision is coming out. Genetic algorithms working in a similar kind of way. There's a solution process going on there, and there is a population of solutions that you can kind of analyze, but you really have to be an expert in the algorithm to know what's going on. Now, if you're just trying to make use of it for an optimization problem, for your applied problem, how do we know that we can actually trust the answers that have come out at the other end? Well, one approach is just to put a human in the loop, right? So you could just run every solution by an expert, but that's got a couple of drawbacks. I mean, it kind of defeats the point a little bit, because ultimately a lot of these problems are complicated enough that you can't solve them very easily by hand. The whole point of using the machine was that you didn't have to do that. Maybe you can analyze the solution by hand, and that's a little bit easier. But it'd be quite good to have a helping hand. What was the decision-making process that was going on in behind the scenes? So this is where what's called explainability comes in, and it's certainly a hot topic in machine learning for deep learning models, as I mentioned. It's all about opening up these black boxes so we can see the algorithmic process that are going on inside, or at least some kind of an idea what caused a decision to be made in the way that it was. So the big question here is, how can we do this for search and optimization? And I think a lot of practitioners in our field are doing this to some extent, but there isn't really a single approach. There's not really a formal way of going about doing it. So I'm going to share a few examples of the kinds of things that I've been doing on applied problems, and I hope this is kind of enlightening. I hope it provides some kind of inspiration for others who are using these tools. So to begin with, we want to ask ourselves what's actually needed to make a good solution. So explainability for optimization, there's a number of different aspects, and one of them is just, why is a particular solution good? How has the algorithm decided that this solution is better than all of the other ones? So what's needed to make a good solution, at least as far as the algorithm is concerned? Does that differ from what the human thinks? And it'd also be good to know how that solution, how the solution that's been generated satisfies those criteria. Another thing we might be interested in is just how robust the solution is. So very often we will get some kind of random noise that's come in the generation process. As I hope I illustrated in my example before, there are random processes going on here. So sometimes we get little artifacts in the generated solutions. It might be a person, I don't know, working on a Sunday instead of a Monday in a schedule, or I'll see a couple of examples when I get onto my buildings problem. Can we tweak or adjust the solution if we don't like some of the bits of it? Or maybe there's just something aesthetic about it, or maybe two people are working a shift and it would be better if they were working opposite shifts, and we'd not encoded that in the definition of the problem. It'd be good to know if making these kinds of changes will affect the solution quality. How might solutions break if circumstances change slightly? So let's say something has been designed for a particular weather pattern and suddenly it's a very warm year. How is that going to impact on things? So these kinds of questions can all be answered by just looking at the relationships between the variables and the objectives, at least as far as the algorithm has understood them. Now, the concept of explainability here is going to be a little bit different to the kinds of things that you might have seen for deep learning. My approach has largely been rooted in visualization rather than natural language, which is where a lot of explainability work's going. I think there's probably room for natural language here as well, but that's beyond my capabilities. So the idea here is going to be to show a little bit about what the algorithm has understood, the key things about the problem are. And hopefully, by giving the end user, the person who's submitted this problem in the first place, by giving them some kind of extra analysis about what makes a good solution good, that might give them some increased trust in the solutions that have been returned. So there's a few ways to do this, and the first one, and actually this is featured in a lot of my work, is mining what's called a surrogate model. So step back for a moment again, and this figure here shows you a very high-level view of an evolutionary algorithm workflow. So if you were paying attention before, you can hopefully kind of map things onto this diagram that I have here. On the left, we've got an evolutionary algorithm, and it's generating solutions. And on the right, we've got some means of evaluating those solutions. It might be a simulation, it might be a bunch of mathematical functions. And whatever it might be, it's computing the quality of the solutions and returning that fitness to the evolutionary algorithm. And then the evolutionary algorithm uses that feedback to generate more solutions until it comes up with something that hopefully is close to being optimal. Well, a surrogate model is a technique that was first introduced to cope with a situation where this fitness measure, the simulation, is very long running. Surrogate model basically is bolted onto the side of the framework like this, and the idea is that we use machine learning to learn what good solutions look like. So the evolutionary algorithm has generated some solutions. It's used its fitness function to estimate the quality of those solutions, and that's some training data. We pass that over to a separate model that we call a surrogate. That model learns to be able to make predictions about what the fitness function would say. And then the idea is that we would swap out the calls to that costly fitness function in the middle with calls to the surrogate fitness function. So by that way, we speed up the optimization process. But there's an extra nice thing going on here, and that is that the surrogate is an explicit model of our fitness function. We've got another thing now that we can interrogate. We can maybe apply some of these techniques from explainable AI to our surrogate model because they are targeted at machine learning models. Or if we use an interpreter model for our surrogate, then maybe that'll provide us with something very helpful in order to understand what's going on with the problem. So that's the idea. We've got this model. We've got it essentially for free because we were using it to speed up the evolutionary algorithm, and hopefully that surrogate is a bit more interrogation friendly. So let's see what that looks like in practice. Some of my earliest work was using a surrogate model like that that's based on what basically amounts to a linear model. It connects the variables or groups of variables to the fitness function. And this model is known as the Markov network fitness model. It's basically a probabilistic model that takes variables and relates them to fitness. And I'll give you a little example to show what that looks like. Let's say we've got a very simple optimization problem, and we can represent it as a graph structure. So over on the right of the screen, you can hopefully see a little network, a graph of 4 nodes, 1 node for each variable, and they've got edges connecting them. And those edges represent some kind of interactions between those variables. So maybe 2 things that need to happen at different times in a schedule or something like that. And the model can be represented as just a linear sum of terms, 1 term for each of the variables. So that top row of that equation there is 1 term for each of the variables. And then the next 2 rows are terms for the 2-way and 3-way interactions between the variables. So hopefully you can see the first one is the connection between variables 0 and 1. Next term is for the connection between variables 0 and 2, and so on. And then the bottom two there are for the three-way interactions, the kind of triangles there. And as I mentioned before, it's essentially a machine learning process. We take a population and we use that to compute the unknowns in that equation, the alphas there, basically the weights that are attached to each of those terms. So that, oh no, I thought I had an example of doing that, but I don't. You'll need to trust me for it, but we take a population of known values for the x's and for the f of x, the fitness, and then that gives us our alpha values, our parameters. Now, this is a linear model. Those alpha values tell us something about what the optimal solution should look like, but they also tell us what the weight of each of those terms are, how important they are in order to optimize the problem. So if we try it for a few toy problems, so this is a surrogate model that was fitted to a population of around 120 solutions for the toy problem that I used in the example at the start, what's known as the 1max function. Now, that there that I have on the screen is a bar plot with error bars on it. So there are 100 bars because it's a 100-bit version of the problem. And so there's 100 variables, and there's a parameter value here for each one of the variables in our problem. And you see that they're all negative, and they're all roughly the same value. Now, I'm not going to go into a lot of depth about how the probabilistic model relates fitness and variables, but basically a negative value means that the optimal solution for this problem should have a 1 for that variable. So what it's saying is the optimum for that problem is that it should be all 1s, and all of the variables have got an equal weight, they've got an equal importance. So this model, which was trained on a very small number of solutions, about, as I said, 120 solutions, has already picked up something very fundamental about what needs to be understood in the problem to solve it. Now, it's a very simple problem, but that's the idea here. It's to try and get a very clear picture that there is some kind of a relationship between the model and what makes a good solution. Stepping it up a little bit, I've tried looking at other toy benchmark problems as well. There's another problem that's basically used to test the ability of evolutionary algorithms to find interactions between variables. So in that previous problem, each variable has got no interaction with any other variable. It makes an equal contribution to fitness, and it should be a 1. But in what's called the checkerboard problem, the goal there is to find a solution that is, if you rearrange it into a grid pattern, is either all 1 0 1 0 and so on, or 0 1 0 1 0 1. So you end up with a checkerboard. So if you imagine the black here being 0 and the white being 1, those are the two optimal solutions on the screen. And the point here is that the fitness function basically counts how many neighboring cells in that grid are opposite in value. So it's introduced some kind of interactions between the variables. And if we look at our surrogate model for this problem, I've got two plots here. So the one on the left is the terms from the model for the absolute values for the variables. That is, should each value be a 1 or a 0? And you can see that they're all floating around 0. Basically, that's saying the algorithm doesn't care whether the values are a 1 or a 0 at all. And that's right, because the two optimal solutions are complete inverse of each other. And what's more interesting from understanding this problem perspective is that on the right, we have what we call the bivariate coefficients. So basically the interaction terms between the variables. And here we can see that they've all set out quite strongly positive and very consistently. So the error bars, I should say, are from repeat runs. It's a little while since we did this now. I think it was from 50 repeat runs of the algorithm. So this is the model coming out very consistently every time, saying neighboring solutions have got neighboring variables have got this positive parameter associated with them. Positive parameter means they should be opposite in value. So again, the algorithm has picked up something very fundamental about solving the problem. Now, you might be wondering why some of the some of the bars are twice the height of the others. I wondered that as well. It's really very neat. Basically, those terms correspond to the red dotted ones, the ones in the middle, basically the ones that have got the biggest influence on fitness. If you can imagine, if you change a variable in the middle of that grid, it's got a bigger influence because you've got more connections coming off it. The ones at the edge don't matter quite as much in terms of fitness. So this model has picked up something about the direction that variables should be going in to make an optimal solution, but it's also picked up something about the importance of variables. So some of the variables matter more than others, so might be a bit more open, a bit less open to being adjusted in a solution at the end. Right, so we now move on, because the toy problem is all well and good, but I think it's much more interesting to look at some real tangible real-world problems. So I've spent a number of years working with civil engineers using these algorithms to optimize the designs of buildings. Primarily, and there is a sustainability angle here, primarily it's about minimizing energy consumption. So buildings take a lot of energy to heat them, light them, cool them, and by and large, we want to make them as efficient as we can without spending lots of money. So we've got a multi-objective optimization problem right there, where we're trying to find a trade-off between not spending any money, but also not using a lot of energy to run the building. And one of the simpler problems I've looked at is to do with placing glazing on a facade. So the building, the office building that you can see illustrated there, has got a wall on it, and we divide that wall up into an 8 by 15 grid of cells that we might glaze. So we might have glass in them. And a minimal energy solution that was found by an evolutionary algorithm on this problem came out as the one that you can see in the middle there. This very odd shape where the blue is glass and the white is concrete. And there's certainly something strange going on here. Basically, the genetic algorithm hasn't completely converged, or it's found a minimal energy solution, but because of the random processes that are going on in generating it, it's got stuck on something that's a bit of an odd shape. Now, we didn't include anything in our fitness function for the shape, and actually it's only at the point that we've seen this window that we think, actually, that's a very strange one. No architect in their right mind is going to commission a building that's got a window that looks like that. So maybe we want to tweak it a little bit. We might want to adjust the solution retrospectively, now that we know that it's in the ballpark, it's in the vicinity of being a very efficient solution. We tried a number of approaches to this. The first one was much simpler than the kind of thing that I was describing before with the surrogate models. It was simply to do a local walk around the solution. So it was to take that solution that we generated and then try flipping each one of the cells from either glass to not glass or from not glass to glass, and measuring the energy consumption again. So the energy consumption here is being estimated using a freely available simulation package for building performance. And this plot here, this heat map that you can see, the dotted line shows the original solution, and then the color and the arrow in each cell gives an indication of the change in energy consumption resulting from changing that cell. And you can see that if we change majority of the cells within the solution from being glazed to not glazed, then we get an increase in energy. So we are pretty close to a minimal energy solution. And actually, that's the case for all the cells around the bottom that were not supposed to be glazed as well. But you can see that there are a small number that if we were to flip them, then we would get a decrease in energy. So that's good in one sense. So many people do combine a local search like this with an evolutionary algorithm to get a slight improvement on their results. But you can see also that some of the increased arrows, so I'm hoping if I can get my mouse pointer back, there we go. Over on the kind of top right, where we've got that big gap in the design of the window, there is an increase in energy from changing these cells here, but it's a very small one. So we might actually decide that we're going to change those ones anyway, so that we've got a more aesthetically appealing window, a nicer looking building, while not really sacrificing very much in terms of the energy consumption. Now, the one downside with this is that it needs further fitness evaluations. And for many of these building performance simulations, there's a lot of kind of movement of energy from one surface to another within the building, movement of airflow, and so on. These are quite long-running things, and they can go from a few minutes to a few hours per evaluation. And if you're working to a deadline, you might not be interested in spending that long letting your machine run. So this is where this surrogate modeling approach comes in again. We used a surrogate model to speed up the optimization run, and our surrogate model, similar to the checkerboard problem that I was showing you before, had a grid structure. So we're looking at the interactions between neighboring variables. We're also looking at the values of the variables themselves. And the model that we got out at the end had coefficients for each of those things. So here I've just plotted them in the same plot, a little bit lazy, I guess. But the ones on the left, the kind of high up ones, you can see that there is a bit of an upward trend there. Those cells are for the windows, the individual cells glass, whether they should be glass or not glass. And the ones on the right are for the interaction terms, so whether neighboring cells affect each other or not. And actually you can see that they're all floating around 0. So there doesn't appear to be any connection between neighboring cells of glass. It doesn't really have much of an impact on the overall energy consumption. Now, from a building physics point of view, that does make a little bit of sense. It might be an indication that there's something odd going on. There were a couple of other problems that we looked at in a similar way where there were rooms next to each other that had no impact on each other. And actually, it turned out that we'd just defined the problem really poorly. We'd forgotten to connect the air conditioning system to the neighbouring rooms. And that's why there was no relationship. So having that kind of that kind of information out of the process, very helpful in understanding that we've made a mistake in formulating the problem. But for this glazing problem, it doesn't matter quite so much. We wouldn't expect that the neighbouring cells would have so much of an impact on each other. But in order to see things a bit more clearly, let's arrange them into the grid structure. And here we've got a heat map again, showing where glazing has got the most impact. And basically the red cells are saying we should put glass here. And the blue cells are saying don't put glass here. So we've got a recommendation that glass is being put in the kind of upper, maybe slightly right, but upper center of the facade. And that makes a lot of sense because the higher up it is, the more light can come in, so we don't have to run the electric lights. But we haven't covered the whole facade in glass, so we don't get incredibly hot during the summer when it's sunny. So there's a couple of ways that we can mine a surrogate model in order to get an idea of the impact of the different variables on the optimization problem. So these plots that I'm showing you here are generated using evaluations from the model. And it comes from free. It comes for free, essentially, because the surrogate model has been built alongside the evolutionary algorithms run. Now we can see the importance of each variable, and through that we can justify the solution that was generated, and we might be able to tweak it slightly if we want. So this is all very helpful information. It's basically what's coming out here is what the algorithm has understood to be the important characteristics of the problem. Sometimes they might misalign with our understanding of the problem, and if that is the case, we go back and we investigate further. But sometimes they are enlightening enough that we think, actually, that's why that solution was chosen. I can understand that. So I'm a bit more willing to accept it. I think at this point, because I'm about to move on to the work with KLM, I'll just stop because I can see there is a question has popped up in the Q&A. So let's have a look at that.
Yeah, there is a question indeed from Evelyn, and the question is very specific. It's regarding slide 20, and it goes like that. Why are the error bars of the first toy problem in slide 20 skewed?
Why are the error bars skewed? I suppose they are ever so slightly. That is a great question. Oh, yes. So they're skewed. So they're just slightly more down than they are up. I cannot answer that question. I'm not completely sure. I'd have to go back and look at the original distributions and try to determine that. My Oh, I wonder if I can guess. So closest to -1 would suggest more likely to be a 1. It's probably that the algorithm is if over the course of its run, the population has become more and more biased towards having lots of 1s in it. So even though it was a fairly short run that produced this, the data will have been biased. And that is kind of one of the points here, is that the models are being built from biased data. It's biased by what the algorithm has seen. So the majority of the models will be seeing higher fitness solutions rather than a uniform sampling of the space. That's my guess, but I can't answer that question categorically. That's very observant. Good question. Thank you.
Well, that's all for now. I guess we can continue, and then we'll have the questions covered at the end.
Right, we'll jump on to the next part. So the next part here is some work that I did with Jeroen shortly after coming to Stirling. It's hard to believe it's been a good few years since we started this, and it was basically working on automated parameter tuning for an existing piece of software. So there was piece of software called Opium. I gather that it's no longer in use at KLM, but basically the job of Opium was to evaluate flight schedule and estimate possible delays. It was basically testing the robustness of the flight schedules. And it's a simulation package, so it runs over a period of 3 months with probability distributions driving things like breakdowns or other factors that might upset or cause disruptions in a schedule. And our goal was to click on PowerPoint and run it. Our goal was to improve the software. So the simulation software had a number of hyperparameters, as many of these modeling tools do. We were set the task of trying to improve it for both running faster, but also making it more accurate. So we had historical flight schedules of a number of years showing what had actually happened. So we were going to try to tune the simulation so that it could estimate disruptions better, but also do it more quickly, so that you weren't sitting for several minutes waiting for a schedule to be evaluated before trying a change and then re-evaluating. So just a little bit more of a summary about the software itself. It had 14 external parameters, and these have been manually tuned over a period of several years, and I would imagine that many of the software developers on the call will be familiar with the concept that after a while you settle down to the parameters that you like, and there is kind of a local refinement process going on here, but after a while they become, don't touch this parameter, it's the right value. If you change it, it'll definitely make things worse. So our job was basically stepping back and applying an optimization algorithm to the process to try and find a global improvement to these hyperparameters for the algorithm. So I mentioned we were provided with real-world schedules and results covering a period of 3 years there. And the idea, basically following the same evolutionary process that I gave before, the optimization algorithm is generating parameter configurations, passing those to Opium, which then runs. We measure how long it takes to run. We measure how accurately it reflected the historical data. And the optimization algorithm takes that feedback and uses it to generate a new configuration. And we used a number of tools. So we did use evolutionary algorithms in this. We also used a tool called SMAC, sequential model-based algorithm configuration. There's a link, a reference down at the bottom there. It's a really nice tool. You can write a Java or Python wrapper for your target application, and you provide a configuration file to SMAC saying what your hyperparameters are, so just the names and what the ranges of them are, and it will then execute an evolutionary process. So it's kind of like a Bayesian optimization that SMAC follows. It builds a model of that estimates the fitness of the target application, and then samples that model to generate new solutions. So internally, there is essentially a surrogate model. We'll see what the impact of that is in a moment. But the approach that we followed here was to apply SMAC to Opium, and initially we were just trying to improve the accuracy. And these numbers won't mean very much, but we managed to improve on the accuracy. We had a mean square error over the historical data, and we got the mean square error down from 271 to 241, which was very nice. But I mentioned that we had a surrogate model essentially at the core of this algorithm. And another nice thing that comes with the SMAC tool is that it'll you can sample that surrogate model. So there's a process that's known as functional ANOVA, and it basically follows this procedure here. So assume that we've got a surrogate model, we've built a model of our target fitness function, and we've got a set of variables that are the variables from our optimization problem. And we want to know what the impact of one of those variables is on average across the space. So let's say we're interested in variable 1. We'll have a few solutions with variable 1 being a 0 and a few with variable 1 being a 1. And you can extend that, right? If it's a continuous parameter, you might have several values here kind of going up in increments across the range of the variable. And then for all of the other variables, you just have a uniform sampling of the space. So see here, for variable 1 being a 0, we've got a mixture of values for variables 2 and 3. And you can use a Latin hypercube or just a uniform random sampling of the ranges for these variables to generate these points. Now, the SMAC tool actually will do all of this for you. But this is the process that's going on underneath. And the idea is that we try these, we test them against the model. So when I say fitness there, that's the surrogate model's estimation of fitness. And you can see that it's estimated a 10 and a 15 for variable 1 being a 0, and 20 and a 25 for it being a 1. So we've got an idea here of the average fitness for each value that variable 1 can take. And we can extend that to look at all of the variables in our problem. So these are the plots that we generated for the tuning of this Opium application. And there were a number of parameters that it turned out actually didn't really have much of an impact. So an example there is this one in the middle. It looks like there's very large error bars. So across the piece, whether that's false or true, whatever's going on there is clearly dependent at least on lots of other variables, but that particular one doesn't have a very strong direct impact on fitness. But other variables have clearly got a much more direct impact on the fitness. So this create gamma. If it's false, we've got a fairly high error rate. So performance here is mean squared error. So we're really trying to minimize it. True, we get a much better value. Very much so the case for this swap measure on. You can see that there's quite a large drop in overall error rate there as it goes from false to true. And we can take that over continuous parameters as well. So the red line here in the middle is the mean, but remember there was a sampling process going on there across the space. So we've got a distribution. So we can have a standard deviation either side or an interquartile range. And so that gray area there is the standard deviation across the space. So we've got, again, an idea of the trend of these continuous variables with respect to our performance. Nice thing that came out of this was that this ground factor out, the initial range for that, if I remember rightly, was between 1 and 1.4. And it was typically set around about 1.2, 1.3-ish. And it was felt that it really shouldn't go beyond that. And the really nice thing about it was that we'd opened up the search. So if you're doing an optimization, it's worth doing this, extend the ranges of the variables and let the search algorithm take a lot of the strain in terms of finding the right range. And you can see here that there's quite a big jump in fitness around about that kind of boundary region that was there before. And then it settles out. And this provided a really nice explanation for why our optimization had pushed ground factor out to around about 2, right into the middle of the safe zone where the error rate was quite low, and definitely beyond that initial higher error range region. I can remember there being a little bit of surprise that we'd recommended a value of that, and then this made sense of that. So that's the kind of insight that we're looking to try and gain from the process, and it's very clearly expressed in terms of the actual target application. So that's great. The process there is giving us a very clear relationship between each variable and fitness. It's giving us a reason for stepping outside the recommended bounds. I mentioned before that it was actually a multi-objective problem, so we were looking at time as well as accuracy. Multi-objective problems, basically the same kind of idea. We're still trying to optimize things, but now we're trying to look at optimizing more than one thing, and often they conflict with each other. So classic things will be cost versus performance or something like that. And the goal here is, again, about giving the user an informed view, but here it's about trying to identify a sweet spot on the trade-off. So there's a generic problem that I've got plotted over on the right here. Each one of these X's is a solution to the problem, and it's plotted in terms of the objective. So in this case, it's energy consumption and capital costs. So you want to make both of these things smaller. Well, if you'd have just decided what your relative weighting of these things was before you started and just tried to optimize them both together, you might have picked a poor weighting and ended up with a solution maybe around this point here. By seeing this trade-off and seeing that there's a big jump around this point here on the bottom right, you immediately have got an informed choice about what solution would be best out of the set that you've been given, because you wouldn't pick that one that's around about 42,000 on the energy, because you can get quite a big drop down to below 39,000 in energy with hardly any increase in capital costs at all. So that trade-off in itself is a very useful thing, but it's also, again, good to see what drives the trade-offs, what parameters are important. So this is jumping back to the problem with Opium, with KLM's software. And here we'd ran a multi-objective genetic algorithm, one called NSGA2. It's a very well-known one in the community, and it's been around for a good long time. It's still very good for optimizing two objective problems. And basically the plot that we have top right here is what we call our Pareto front, basically the set of solutions that we produced at the end. And the red dot is the default configuration that Opium came with, and the blue triangles are the optimized points. And you can see that there's a few triangles there that are smaller in runtime, so they run faster, and they've got a lower error rate, so they're kind of down and left from the default. So we've improved on both of the goals, but you can see we've got a good range of different configurations. If we want to increase the accuracy by a lot, we might take a hit on the runtime. But if we want a really fast running simulation, we know now what the impact on accuracy is doing that. And we presented a number of plots to the developers of Opium, like the one at the bottom, where we can see each row represents a solution, and they're sorted in order of the objectives and goals. So the objectives are on the right, mean squared error and runtime, and you can see over on the left are the variables, and I think, yeah, that's all 14 of them. So you can see which ones have got some kind of an impact on this trade-off and which ones don't. So let's see, the very first one, MMR, looks like it floats. There's a lot of random noise there, probably doesn't have very much impact. Whereas the later one, so SMO, which is way over on the right-hand side, has got a very clear step change as we go from long run times, high accuracy, to short run times, low accuracy. And then there's some other variables, like this CG, which is about sixth from the end even, which is kind of a secondary driver variable. So we can see that it's of secondary importance, and when SMO changes from 1 to 0, then it jumps back. So it's got kind of a cyclical thing going on. So again, we've got some kind of an idea of which variables are driving the goals, and if that has got any impact on our decision-making process about which one we pick, then we can make an informed choice about that variable. Right, I'm very nearly done. I've got another little demo to show you, and then we'll be able to move into questions. Now, I'm going to present this because I think it's really nice. I've used it in some of my own work, but it is not my original research. This comes from a group at Edinburgh Napier University, named down at the bottom there. basically, what they're doing is using what are known as quality diversity algorithms or illumination algorithms. And the idea here is it's a genetic algorithm that is still trying to minimize costs. It's trying to find a good high fitness solution, but rather than just one, it's now trying to find high fitness solutions that have got a lot of diversity to them, that cover the space of variables very widely. And the particular algorithm they're using is called Map Elite, and they used it for a transportation problem. Now I'm going to show you an example for a buildings problem. Basically what you get at the end of this run is a whole set of solutions that span potentially multiple objectives, but also are very diverse in terms of the variables. So then you can make a choice at the end about your other kind of preferences that weren't included in the objectives. And what they found with their industrial application that they worked on is that by involving the users in making that choice from a range of solutions that they know are all roughly the same quality, they've got more confidence in the results because they've been involved in the decision making. So I'll jump over to the interactive decision making tool. So you might be able to see the URL at the top there, so you can play around with this yourself if you wish. But what we have here is what's called a parallel coordinates plot. So each one of the lines on this plot represents a solution. So each one of these wiggly lines that are kind of going from left to right is a solution. And the vertical lines on the left are variables in the solutions. Over towards the right are objectives. So these are things that have been influenced by the variables. So this is for a building problem. So you can see there's heating set point, glazing ratio, construction types of walls and ceilings. But then over on the right, there are things like how often does it overheat in the summer? How much energy does it take to run the building? What's the capital cost of it? And you can see that some of those objectives have got an inverse relationship. So energy versus cost, very much opposing things. And the nice thing about this is we can do, again, an iterative decision-making process. So you might look at this and go, well, there's quite a big step change in energy, similar to that trade-off that I showed you before. So actually, we'll just keep things that are below that step change in energy. We'll drag out a box around those and we'll keep those solutions. And then actually we note that there's still a range of overheating times here. So we'd like the people in the building to be comfortable, so we'll keep maybe the bottom half of that range. And then actually it turns out that this wall type, there are 3 different types of concrete being used to build the wall, and the one at the bottom is the easiest one to work with, so we'll only keep those solutions. Now we've narrowed it down. We've got a very narrow range of buildings now, and we can see that there's a spread of costs. Well, ultimately we want the building to be cheap, so let's pick the cheapest one. And now we've got one design. And we've narrowed down our process by kind of interactively defining really what our problem was about. So although we wanted to minimize energy and cost overall, and we got a good spread of things in that for those goals, there were other factors at play as well. And now that we know that we can accommodate all of those, we've been able to step through and choose a solution in an informed way like that. So let's see, I think that's the end of that demo. That's that Pareto front again. So briefly summarize. The idea here is that we can explain the optimization results, at least to some degree, by exploring how each variable drives the objectives, the goals, fitness, and how those variables interact with each other. We can visualize these things. We can do it as part of the optimization or as part of the final results. Point is, that by knowing which variables are important, which variables are sensitive, we can adjust the solutions, factors that we hadn't considered during the optimization, and we can see where the algorithm's found a loophole, where it's exploited some gap in our problem definition. And by giving the user an informed choice in the solutions, it'll increase their trust. I've given you a few different approaches here. Very much early days as far as my research is going on this. I think a lot of it is very highly problem specific. So we need better ways to automate the process. As I mentioned before, natural language generation would be a really neat thing to include in this too. So being able to say things like, I picked that solution because this variable was important. You know, things that will not require someone who is happy with visualizations to be able to engage with. Now, you might be wondering whether, and this is very much an open question, is this explanation or just justification? I would argue, well, that doesn't really matter so much. The point here is that we're trying to provide some kind of illumination into the algorithm's decision-making process to help people make good choices and take up the results, the optimization. So that's the overall goal of what's going on here. I hope you found that interesting and helpful. I'll now open up for questions.
First of all, thank you very much, Sandy. That was very, very interesting. Very technical as well, but I think you presented some really great examples of how can make use of the different algorithms, and well, I think it was very indicative of the type of the problems we can approach, and very interesting. Thanks a lot.
Thank you.
Let's see. Well, we have no new questions so far, so I'd like to invite the attendees to post their questions in the Q&A section. So Sandy can answer them. Well, by that time, well, maybe Jan has a question, for example.
Yes, if there are no questions yet, I have one question myself. So what I understood from the first part of your presentation, that's about this surrogate. So it's really cool idea, concept. So basically, it's kind of a pattern that you try to detect to explain your fitness function. Understood
Yes.
things correctly. And then I think you use the surrogate to, well, have your explainability in place. So my main question then, and maybe it's a stupid question or a naive question, but would it be possible to have, let's say, two different surrogates? They really fit your fitness function, but that gives almost opposite explanations. So there's a kind of underlying assumption on your side that, let's say, there's only, let's say, one best surrogate, and I was wondering about that.
Yeah, that's a great question. I've got a PhD student who's looking at this just now. So what he's trying, so what I presented there was this largely focused on that linear model, and an obvious criticism there is maybe that model is not getting a very accurate picture. So what he's doing is trying a lot of more contemporary machine learning approaches and comparing the kinds of things that they're coming out with. So are they ranking the variables in much the same way? Are they giving the same kind of measure of importance to each one? Are they detecting interactions in the same way? So far, the evidence would be that they broadly get the picture right. There is a little bit of noise. The kind of top 3 or 4 variables in a problem will sometimes be interchanged with each other. But broadly speaking, if a variable doesn't matter, they pick that up, and if it does matter, they do pick that up. One thing that we were trying was interpretable models, things like decision trees. Turns out they're not quite good enough. They do pick up some of the structure of the problem still, but just they miss too much of it. So we are unfortunately stuck in kind of random forests and neural networks and things that you then need to retrofit explanations onto again. So there's a lot of layers of complication going on here, unfortunately. But that is a very good point, and it's something that we're investigating just now.
You already answered my second question, but thanks. I was wondering about the surrogates and how complicated they could be, because at some moment it looks like kind of neural network modeling. Yeah. These are my questions for the moment. Thank you.
Well, thanks, Jeroen. In the meantime, we have a new question. That's from Armon. And the question is, have you done any evaluations with end users?
Me personally, no, and that's a very obvious gap. The end user broadly, there's been some anecdotal stuff. So the buildings things, we had an industrial consortium that we were working with, and some of the plots we shared with them, and they found it helpful, but there hasn't been any real qualitative analysis done. I know that the people I cited towards the end, Urquhart et al. at Edinburgh Napier, I know that they've done a little bit of work with end users. But again, I think we really need to do more in that way. I'll admit right now, I tried to get some money to do such a study fairly recently and didn't get it. So if anyone feels like funding one, that would be very helpful. But no, we haven't, and I think that is very much needed, and that one of the problems with the explainability community at large, and I'm obviously guilty of this as well, is that we've been at the moment just trying to find out what's possible in the way of explanations. I think we need to do a bit more work in the way of what's needed.
Okay, that's clear. Thanks. Well, not sure if there are any other questions, or that's it for now. Well, I guess yeah, that's all for now then.
Okay. Well,
Yeah, I think that's us.
I'll just take over for some closing words. So, first of all, Sandy, thanks again for this presentation. Technical, but very interesting, at least for me. So I really enjoyed things. Maybe then one remark for our next session. So that will be on Tuesday, July 13th. And that's called Privacy Attacks of AI Learning and Algorithms. And will be presented by Saba Amiri. He's currently working as a PhD at the University of Amsterdam. So in 2 weeks from now, we have, let's say, another webinar coming up. So thanks all for attending. I will now stop the broadcasting, and hopefully I will see many of you next time. Thank you.
Thank you.